with a thesis in experimental nuclear astrophysics carried out at the NFL National Laboratories of the South. In 2008, he completed his PhD here in Ferrara with a thesis on an experimental study of the proton structure within the Hermes experiment at Crisi. For this work, he received 2 national awards from the Italian Physical Society and the INF. Then he continued his academic career in Ferrara throughout 2 various research positions, and has been associate professor since 2021. Since 2018, he has been teaching particle physics for the master degrees in physics and general physics for the bachelor degrees degree in chemistry. He has served as the local coordinator of INF-3 for 2 terms, and since 2025, he is a vice coordinator of the PhD program in physics. He is currently involved in 2 particle physics experiments at CLAS-12 at JW and LCD experiment at CERN. And so today we have the pleasure of hearing him on this seminar about exploring the multidimensional structure of the nucleus.
Yes. Thank you, Stefania. Thank you, everybody, for joining. So, yes, it's my pleasure today to bring you in this journey into the structure of the proton, of the nucleus in general. Since I expected to have some students here in the audience, I tried to make the seminar, let's say, pedagogical and also a bit historical, hopefully not too boring for you. So let me start from what we know today about the structure of matter. Okay, so as you know, the quest for understanding the fundamental constituents of the nature of matter and also the forces that regulate their interactions has driven the curiosity of scientists over the last 2 centuries. And today we know that ordinary matter is essentially made of molecules, which are bound state of atoms. And we know from Rutherford experiment already back in 1911 that atoms are made by a very small, very dense, and positively charged nucleus surrounded at a very large distance by a cloud of electrons. Overall, it is electrically neutral. And then the nucleus itself is made by a compact system of 2 different kinds of particles that we call protons and neutrons. The proton discovered in 1913 by Rutherford and the neutron in 1932 by Chadwick. And until, let's say, the mid or the end of the 60s of the last century, protons and neutrons were believed to be elementary objects, so point-like structureless objects. But now, at least starting from the end of the 60s, we know that actually protons and neutrons are not elementary particles. They are compound systems. They are made from more fundamental objects inside that we call quarks and gluons. And in particular, the proton and the neutron are made by 2 types of quarks, the up type and the down type. And quarks comes with a fractional electric charge, so they carry a fraction of the electron charge. And they also carry an additional kind of charge that is called the core charge, which comes in 3 different states, blue, red, and green, which is extremely relevant for also the theory of strong interaction. So if we focus on the upper part of this figure, and we consider the bound state here, and this is the upper part, then we realize that these bound states are driven by the electromagnetic interaction that arise from the unification of electric and magnetic phenomena, as it was already beautifully understood by Maxwell in this Maxwell equation. And then the theory of electromagnetic interaction has evolved and has expanded into the realm of quantum mechanics and of special relativity, and has further evolved into the modern quantum field theory of quantum electrodynamics. And it is, of course, responsible for a lot of fundamental phenomena at the scale of atomic and subatomic scale. And as far as we understand, the electromagnetic interaction between 2 any charged particles occur through the exchange of a photon. But now, if we focus ourselves on the bound state in the bottom part of the figure, then we understand that there is a different fundamental interaction, I think here, that we call the strong force, which at the scale of the nucleon size is more or less 2 orders of magnitude stronger than the electromagnetic interaction, which is a good news for us, for everything, because this strong force keeps bound the nucleus against the Coulomb repulsion due to the fact that protons are all positively charged. Then, a very important difference with respect to electromagnetic interaction is the range. The electromagnetic interaction is an infinite range interaction. Instead, the strong interaction has a very, very tiny range of the size of the proton, essentially 10 to the minus 15 meters. And it is mediated by different kind of particles that we call gluons. And the interaction at the fundamental level occurs between quarks. That's because they possess this additional charge, the core charge. Okay. And the theory that explains all this and that allow us to understand the strong force is another quantum field theory that we call the quantum chromodynamics, or CPQCD. So back to our understanding of the structure of matter, we think, of course, we reached today the most fundamental level in nature, okay, where the proton is made by 3 quarks, which is actually not the case. If we look more carefully at the structure of the proton, then we understand that protons and neutrons are not just a bound state of 3 quarks, but are rather much more complex systems, including valence quarks, C quarks, antiquarks, and gluons, and all these things move with respect to each other and interact among themselves in a non-trivial way. So the key question we want to raise and we want to answer actually is, how do the basic properties of the proton, like the charge, the mass, the spin, the magnetic moment, arise from this gargling microscopic worldview? And if you want to answer this question, of course, we have to study in detail the degrees of freedom of the nucleon. So we need to study, to access quarks and gluons and study their dynamics inside nucleons, inside the proton, for instance. Which is, however, not an easy task. One could naively think, as it was already thinking in the, let's say, until the mid of the last century, that one could access quarks and gluons by simply smashing 2 high-energy protons, okay? And then if the energy is large enough in the collision, the 2 protons get smashed, and everything that is inside can be observed as free particles. So one can look for free quarks or free gluons, which is unfortunately not the case. And this is due to a peculiar property of quantum chromodynamics that we call confinement, that essentially prevents objects carrying color charge to propagate freely in space. Due to confinement, they are instead forced to be confined indeed within atoms. So, for instance, within the proton. So this is not a good idea if you want to study the internal structure of protons, not at least in this way. We will come back to this later. But the good idea is actually to perform scattering experiment, which is not an original idea. This was already done by Rutherford back 1 century ago. And the idea of Rutherford, you know, everybody, is very simple. So he was using the source of radioactive nuclei to produce a collimated beam of alpha particles impinging in a gold foil. So he wanted to study the interaction with the alpha particles, which are helium-4 nuclei, with the atoms of gold. And then the idea was to look at the angular distribution of the scattered particles after the scattering in the final state. And surprisingly, as you know, he found that some of the particles were backscattered or scattered at large angles, and this allowed to reject the existing model of the atom by Thomson and to propose a new model, which is the planetary model. But this is all story. The point is that we can use the same technique if you want to explore now the nucleon structure instead of the atom structure. So, for instance, we need, of course, to select a proper probe to do so. And electrons turn out to be ideal probes for this kind of scattering experiment for at least 2 reasons. First of all, because, of course, they are electrically charged, so they allow, by studying the angular distribution in the final state, so after the scattering process, they allow to essentially study the distribution of electric charge inside the proton, how the electric charge is distributed inside the proton. But there is also a more practical reason. And the point is summarized in this picture here. So, of course, if you want to study the proton, we want to do this at the maximum how to say, precision. So we want to maximize our spatial resolution. Okay, we want to observe features smaller and smaller inside the proton in order to get the full picture. And in order to do so, okay, we need, of course, a small de Broglie wavelength, so we need high momentum. And so we need, in other words, high energy electrons. And the good thing is that since electrons are light particles, ultra-relativistic electron beams are relatively easy to obtain in any experimental facility. Okay, so there is also this practical reason. So the idea, in fact, is now to study the structure of protons by using a very high energy electron beam, and this is what we call the deep inelastic scattering. Deep because now the energy involved here is very high. It is, of course, an electromagnetic interaction in this case between the electron beam and the proton. So again, this happens through the exchange of a virtual photon, which is a high momentum virtual photon. Okay, it's a hard photon, and because the energy involved in the process is very large, and this results in breaking apart the proton. Okay, and so all at the end, the proton breaks up in a bunch of hadrons that can be eventually observed in the final state. But people is essentially focusing in the detection of the scattered electron. So people usually measure the angular distribution and the momentum of the scattered electron, and this already provides a lot of information about the momentum distribution inside the proton. So the first DAS experiments were performed indeed in the late 60s. This is the famous SLAC-MIT experiment done in California. And already by the first results of this experiment, it was clear that the underlying process in electron-proton DAS scattering is actually the scattering of electrons with point-like charged spin 1/2 object within the proton, okay? Which was probably not expected by everyone at the time. And these objects were called partons. However, it was rather soon realized that these partons coincide with the quarks that have already been introduced by Gell-Mann and Zweig in 1964 in their attempt to describe the regularities of the hadron multiplets in the framework of this static quark model. So it is interesting to have a look at the cross-section for this process, for the DAS process. At first order, it looks like in this way. And you can see we can factorize this in two pieces. The first piece is the standard cross-section for electromagnetic interaction among point-like particles, so essentially the Rutherford cross-section. And then all the information about the nuclear structure, everything happens here, is encoded in the second part of the cross-section, which indeed, in terms of these two objects that we call Bjorken structure functions, encode all our knowledge, or better, all our ignorance in the proton structure. So first, we want to have access experimentally to these two objects, F1 and F2, which are related to each other. And we need a framework to interpret our DAS results in order to do so. And this framework is provided by the Parton model. According to the Parton model, the electron-proton deep inelastic scattering is actually interpreted as the coherent sum of individual elastic scattering processes among the electron and each of these partons inside the proton, okay, which are actually supposed to be quasi-free, so essentially not interacting with each other. And this is because everything works in the so-called impulse approximation that I will not discuss now. But an important point here is to say the frame in which this Parton model works, okay? It is a frame where the proton is not fixed at rest, as it is in our laboratory, but it is instead a frame where the proton is moving very, very fast along one direction that we call the longitudinal direction. This is called, in fact, the infinite momentum frame, okay? So in this frame, the proton moves very, very, very fast with huge energy in this direction, could be the z-axis. And so the important thing is that if this is the case, then clearly we can neglect all the transverse momenta, all the transverse component of the momenta of the parton inside the proton, because everything is pushed longitudinally. So that's why we call about collinear partons. So the standard Parton model provides indeed a collinear description of the proton, neglecting all the transverse degrees of freedom. And these, as we will see today later, are actually extremely important. So within the Parton model, we can now interpret these two structure functions, the one entering the cross-section, in terms of these two objects that we call Parton distribution functions, or PDFs, which depend on a variable x that is called the Bjorken variable, which in this specific frame, this infinite momentum frame, can be understood as the fraction of the longitudinal momentum of the proton carried by each single quark or parton. And then capital Q is the charge of the fractional charge of the quark, which M is here squared. So for instance, if we take F2 and we consider four contribution, up quark, down quark, anti-up, anti-down, of course we can also have heavier quarks here, and we weight each with the corresponding square fractional charge, then this is the expression, okay, of F2, in terms of these Parton distribution functions. But then what are partial distribution functions? Why do they describe? So let's take this one, for instance, UPX. This is the partial distribution function of the up quark in the proton, and this essentially describes the probability to find an up quark within the proton carrying a fraction x of the longitudinal momentum of the proton. That's the probabilistic interpretation. And then, of course, we have also from down, anti-up, anti-down, strands, and so on and so forth. So after the early DAS experiments, a very strong boost in the field came, let's say, in the 90s, thanks to this beautiful machine that was operating at the Daily Laboratory in Hamburg, in Germany, that is the HERA, Electron-Proton Collider. Okay, so this is a 6.3 kilometer long machine, circular machine, with two interacting beams. We had a lepton beam made by either electrons or positrons with an energy of 27.5 GeV, and in the other direction, a proton beam with energies up to 900 GeV. And then there were 4 interaction points, 2 of which, okay, were serving these indeed collider collisions, electron beam against proton beam. So as you can imagine, this is a deep energy scattering, very, very deep, okay, very, very large energy. And these 2 interaction points were served by these 2, let's say, general purpose detectors, Zeus and H1. Then there were also 2 other interaction points, which were served by fixed target experiments. So not exploring the beam collision, but beam with target. And I will discuss this later on. So what is the achievement of HERA? Thanks to this beautiful machine and years of operation, of course, it was possible to map, for instance, the F2 structure function in a huge, with a huge kinematic coverage. So here you see essentially the Q square, which is the square of the transfer momentum of the DAS process, which spans 6 order of magnitudes, and this is the X orbital, which also spans 6 order of magnitudes. Okay, so thanks to HERA, essentially we really were able to map the structure function in a very, very wide kinematic plane, kinematic region. But then how can we extract the PDFs? The PDFs are, let's say, our final goal, okay? It's what we really want to measure in order to understand how the proton is made. So we need to somehow extract the PDFs from these kind of measurements, which is not an easy task, okay? Actually, it is done in terms of very sophisticated global fits that put everything together, all the world data together, as much as they can, where, what I mean world data? I mean that one can actually measure PDFs, proton PDFs, in many different processes. We have discussed about deep energy scattering with electron in muon, in fixed target experiments, also in collider experiments like HERA that we just discussed. We can also study neutrino proton scattering, deep energy scattering. In this case, of course, one study the weak charge of the proton, on the inside proton, and this is mediated by the weak bosons, the W and the Z. But, as I was mentioning at the beginning, we can also actually study PDFs in hadronic collision, purely hadronic collisions, proton-proton, okay? And this can be done in 2 ways, either by studying inclusive production of hadrons in proton-proton collisions, or through the Drellian process, which is a very nice process. It's a process where we have 2 colliding protons, and then one quark from the proton and the antiquark from the other annihilate, producing at the end a pair of charged leptons. So, in other words, the study of the PDFs can be done in many different ways, in many different laboratories with many different kind of beam, okay, lepton, charged lepton, neutrino, proton, etc., and in very different kinematic domains. Okay, so the fixed target experiment usually covers this range here at large X, which is the so-called valence region. It is the region where the valence quark are more important. The HERA collider extended this to higher Q square and also smaller X. The Tevatron, that was a proton-antiproton collider at Fermilab, covered this high Q square region, and then, of course, the Large Hadron Collider is covering this huge region here at high Q square and also small and very small X. So, by putting everything together and performing these very sophisticated global fits, people is indeed able to extract PDFs. Okay, and this is more or less what we know today about the PDFs. So here you see the PDF of the balance up quark, the PDF of the balance down quark, and then we have the PDFs of the C quarks, U bar, strange, charm, and so on, and also the PDFs of gluons. This is reported as a function of X Bjorken and at a specific value of Q square, which is not irrelevant because all these objects can evolve with Q square. Okay, this is a QCD evolution. So if you calculate these at 10 GeV or 1000 GeV, you get different distributions. But what are the main features here? Of course, I will not go into the detail, but the main features are the following. So the two valence quark distribution, valence quark means the quark that provide the quantum numbers of the proton, of the neutron, are picked essentially in this large X region, okay, which is needed the valence region. And the integral of the up quark is essentially twice as large as the one of the down quark, which is consistent with the proton having two up quark and one down quark. Then we also note that the C quark and the gluon distribution actually peaks in the small or very, very small X. Okay, so you need high energy to reach this region here. And the other thing that I want to emphasize is the precision of this data. Okay, so the band that you see here corresponds to the present uncertainty, okay, which is very tiny. Okay, so in other words, today we have a very, very precise knowledge of the momentum distribution of quarks within the proton and gluons. About gluons, this curve here, which is the PDF of gluon, is actually damped by a factor of 10, just for representation, to make easy the representation. This means that the real curve here is 10 times steeper, okay? And this can be a problem, and I will come back to this at the end of the seminar. So the message I want to bring here is that, okay, we know essentially pretty well today the momentum distribution of quarks, okay? But now, as usual, when you think you understand something, something unexpected arises, okay? And there is this nice sentence by Robert Jeffrey, who was one of the fathers of the DIS formalism. He said, you think you understand something, this here, then try to add speed, and then MS comes. And I like to pair this sentence with this nice figure, this nice picture of Pauli and Bohr studying the motion of this spinning top. So what's the problem with spin? Naively, there is no problem, in the sense that as it was naively expected until the middle of the 80s, so let's say 40 years ago, it was supposed that the contribution to the spin of the proton, which is 1/2, is a fermion, coming from the gluons is in average 0. Those for the C quark is also in average 0, and so only the valence quarks should contribute to the spin of the proton. And then this is rather straightforward because we have just three valence quarks. If you keep two of them with opposite spin, so they give 0 contribution, the entire spin of the proton, 1/2, comes from the spin of the remaining valence quark, 1/2, and we are done. Very simple. And this was indeed the belief until, let's say, the end of the 80s, until this European Muon collaboration at CERN made the first precision measurement of polarized deep energy scattering, and they actually found that quarks actually contribute only marginally, if nothing at all, to the spin of the proton. And this was completely unexpected. Okay, so this naive expectation was a complete failure. So panic, it was called the spin crisis. And the question now is, if this is not the case, then how does the spin 1/2 of the proton emerges from the spin of all its constituents? We know that within the proton we have the valence quark, C quark, and antiquark, gluons. How do they conspire to get to the proton being a spin 1/2 particle? That's not a trivial question. And to answer this, of course, we needed to perform more precise experiments, and we need a new generation of polarized deep energy scattering experiments, such to measure more precisely, these spin-dependent particle distribution functions. So let me come back to HERA that I discussed before. Okay, as I mentioned, there were also two fixed target experiments. The HERA-B experiment was exploiting the proton beam with a fixed target, and the Hermes experiment was exploiting only the electron beam or positron beam with a fixed target. Now, and the Hermes experiment was indeed designed as one of these new generation polarized deep energy scattering to try to solve this spin crisis. So a good feature of HERA, of any electron storage ring, is that the electrons circulating in the beam becomes spontaneously polarized. And this is an electromagnetic effect called the Sokolov-Terner effect. But in the transverse direction, so in the direction of the magnetic field of the machine here. So in order to make, let's say, polarize these studies, we needed to just to rotate the spin from transverse to longitudinal, and then to make a polarized collision with a longitudinal polarized block, for instance. So this was done at Hermes. This is a picture of the Hermes experiment that was operating from 1995 to 2007. And what you see here, this huge device here, is the polarized target system. So this system here was providing a longitudinally and also transversely polarized proton target, okay? And then we have also a polarized lepton beam circulating around. And then all the rest was, let's say, a standard forward spectrometer. We have the dipole magnet, we have tracking station before, within, and also after the magnet, and then also a PID detector at calorimeters and so on and so forth. Now, why do I spend time on Hermes? Well, because the Ferrara group made a lot of contribution for the Hermes experiment. First of all, we had the responsibility and the operation of this very sophisticated polarized target system, which is now in our capannone Blocco G, because we are now refurbishing this for a future experiment at CERN. And this is a rather complicated stuff. Okay, so we have a first object we call atomic beam source, which provides a beam of nuclearly polarized atoms. This is injected into a storage cell, which is a tube essentially, through which the beam of air is coming, okay, it's passing through, and then we have a diagnostic system to measure the polarization of the gas inside the cell. So the Ferrara group had the responsibility for this very sophisticated device. Not only, it was also responsible for constructing, producing this storage cell. We have made a lot of them here in our workshop, mechanical workshop in Ferrara. Not only, of course, we made also important contribution to that analysis, and also he covered a lot of important role of responsibility within the collaboration, also including analysis coordination. But Hermes was not the only new generation experiment. There is, fortunately, a concurrent experiment, that is the COMPASS experiment at CERN. COMPASS is located in the north area of CERN. Okay, so it is served by, let's say, muon and pion beams extracted from the superposited synchrotron. And it is, let's say, a general purpose, pretty complicated double spectrometer with two magnets, which has done a lot of physics, including also polarized PDFs, so polarized internalized scattering. The tracking was a bit shifted with respect to Hermes, so this started in 2002 and finished in 2022, so it is now in the analysis phase. But there was also a very good overlap between the two experiments. So how does a polarized DAS experiment works? Okay, so it's still a DAS experiment. We have still a high energy electron beam and a proton, but now they are polarized. So suppose this is the polarization, the spin of the incoming electron, okay? Then with our polarized target, we have the possibility not only to polarize the proton in one direction, but also to flip the polarization, so to invert to the other direction, which is absolutely relevant, as you will see in a moment. So let's consider this configuration here, okay? So we have the electron polarizing this way and the proton polarizing the other way. And then by angular momentum conservation, simply, it turns out that with this spin configuration, one is only sensitive to quarks with spin parallel to that of the proton. So we can call this PDF Q+. But then we can invert the spin of the proton, pointing in the opposite direction. And again, for angular momentum conservation, we are only sensitive to quarks whose spin is anti-parallel to that of the proton in this case. And so we can call this Q-. The useful thing is now to combine these two information, okay? So if we just sum them, we are sensitive to the sum of these two PDFs, okay? But when you sum two PDFs with opposite spin, it's like you are averaging the spin. So at the end, you end up something which is unpolarized. And in fact, these are the standard unpolarized PDF that I just discussed 10 minutes ago, okay? That are also called the momentum distribution. But if we take the difference, now we are sensitive to the net polarization of quarks within the proton, okay? And so this provides sensitivity to a new PDF, a new partial distribution function that we call the helicity distribution. It is denoted as delta Q, okay? So these account really for the distribution of longitudinally polarized quark within a longitudinally polarized proton. And there is also another way to make this measurement, which is semi-inclusive DAS. In inclusive DES, one just catches the electron, okay, the scattered electron. In semi-inclusive, one also catches, for instance, one of the hadron produced by the fragmentation of the struck quark. So we have more information here. And this allows to have also sensitivity to the different quark flavors, okay? So one can measure the helicity distribution for up, down, and the up and the down strange. These are results from COMPASS, these are results for Hermes, they are pretty much consistent with each other. And so now we have a handle to try to answer to the spin crisis of the proton, okay? So if we sum up all this contribution and we integrate over x from 0 to 1, we obtain this delta sigma, which essentially corresponds to the contribution to the spin of the proton coming from quarks, any type of quarks. And then in 1988, the EMC collaboration, as I was mentioning before, measured this to be consistent with 0 within experimental uncertainty. But now the new generation experiment, Air and COMPASS, measured something which is of the order of 30%. Okay, so the contribution of quarks is actually non-zero, but it is not even 100%. Okay, so still not enough to explain the proton moment, the proton spin. That is sizable, 30%. So how can we then understand the origin of the proton spin? The proton is a spin one half particle. For sure, we have a contribution from quarks, from the spin of the quarks. For sure, we have contribution from the spin of the gluons. The gluons are spin one half particles, so they also, of course, contribute to the spin of the proton. But then, within the proton, quarks and gluons can also rotate. So they can also contribute in terms of orbital angular momentum of both quarks and gluons. And this sum here is a very famous sum rule. It's called the Jeffrey-Manoir sum rule. Jeffrey is the one that made the sentence before. And this tells us that essentially the spin of the proton is a puzzle made by different contribution, different pieces. One is indeed the spin of the quarks, the spin of the gluons, but also the, let's say, orbital motions of quarks and gluons. And what is the present situation? We know now from this second generation experiment that the quark contributes 30% to the spin of the proton. We know from RIC experiments that the gluon also provide a sizable contribution, order over 40–50%, although with very, very large uncertainties, and data only cover a very small, let's say, kinematic domain. And then just by difference, we can infer that the angular motion, the angular momentum of quark and gluon cover the remaining 20–30%. Now, why did I put this in red? Because this we cannot measure. There is no way up to now to measure directly the angular momentum of quarks and gluons. Okay? There are indirect ways, of course, and I will come to this later. So to summarize, the quark accounts for 30% of the proton spin. The C quark in particular provide a very small contribution. The gluons provide a rather large contribution, but we have large uncertainties here. This comes from RIC measurements. And by sure, there is an important contribution from the orbital motions of quark and gluons. Okay? But this requires, of course, the existence of a non-zero transverse momentum of quark, the one that we neglected in our infinite momentum frame. And so there is something that we must not neglect. So what is the situation today? These are the standard unpolarized PDF that we just discussed, so very large precision. This is the situation now of the helicity distribution, delta Q. We have a rather good precision for the up quark and the down quark, the valence quarks, okay? Not as precise as this one, but still reasonably good. We know that the C quark provides a very small contribution. The gluon provides a large contribution, but with huge uncertainty. And what if we now try to transversely polarize our target? Okay, so we can repeat the experiment, but now with a transversely polarized proton. And this we could do at Hermes and also at COMPASS. Well, in this case, we are able to study another different independent part of the propagation function, which we call transversity, which indeed describes the distribution of transversely polarized quarks within a transversely polarized proton. And it is not just a rotation between the two, okay? Because we have a relativistic effect, which don't commute with the Lorentz boost. So the two are actually completely independent objects. What do we know about transversity? We know something, little at the moment. These are the, let's say, global fit extraction of transversity for up and down quark. Most of these curves are actually extrapolation in a region where there are no data, especially above x 0.4. There is nothing here. We don't have data. And we don't know nothing about C quark, for instance. Okay, so we have only first glimpse here. Now we can accommodate these three PDFs in this table using the modern nomenclature. So this is also called F1, this is also called G1, this is also called H1. Okay, and U, L, and T stands for unpolarized, longitudinally polarized, and transversely polarized quark in this row. Oops, sorry. And proton in this other row. So just to say, the G1 heredity describes the distribution of the longitudinally polarized quark within a longitudinally polarized proton. This is an unpolarized quark within an unpolarized proton, and so on. So these three PDFs describe, as we said, the complementary aspect of the neutron structure. They form a complete set of collinear PDF, and they are indeed all equally fundamental and equally necessary for a complete description at first order of the neutron structure, collinear neutron structure. So I'm emphasizing again collinear. Okay, collinear means that everything is collinear. Okay, that we are still neglecting the transverse momentum component. Beautiful, but collinear PDFs actually provide only a one-dimensional description of the nucleus of the proton. And this dimension is just the longitudinal direction. Okay, everything transverse is neglected. So everything essentially is a function of just one variable, the x variable. Can you imagine going in 3 dimensions? Okay, if you go in 3 dimensions, of course we gain a lot of more information about the structure of the proton. Okay, but of course this requires a completely new paradigm, and I will come to this in a moment. So essentially, passing from 1D to 3D, okay, the amount of information is increasing enormously. And just to make a comparison, this is what happened when you compare brain tomography with the nuclear magnetic resonance compared to the one-dimensional electroencephalogram. Okay, so we really get a lot of information when we move to 3D. So the collinear approximation that we used so far indeed requires only longitudinal degrees of freedom. This is the longitudinal momentum fraction of the quark. Okay, everything is longitudinal. We are completely neglecting any information apart from the spin in this transverse plane. But then if you want to go 3D, if you want to explore these new territories, then we need the transverse degrees of freedom, the transverse component of the momenta that we call this KT or PT, whatever, but also the transverse position of the partons within the proton. And ideally, we would actually go to a 5-dimensional description of the proton. This is given in terms of the Wigner function, which depend on the longitudinal and transverse momentum component, and also on the transverse coordinate, spatial coordinate component. Knowing the Wigner function means knowing everything. You know essentially how the quarks and gluons are distributed in the phase space. You know where they are and how they move. Okay, so this is really the final goal. However, the Wigner function is not directly accessible experimentally for fundamental reasons, essentially for the uncertainty principle. But what we can do is to measure 3-dimensional projection of the Wigner function, which is already a lot. And this we can do in 2 ways. So one way is to look at the tomography of the proton, okay, so the 3D picture of the proton in the momentum space. So what you see here, this is the color corresponds to the density of particles inside the proton, and each of these parallel is the transverse momentum plane, so Kx and Ky, whereas the longitudinal direction is the Z direction. And then one can map the proton density in the transverse momentum plane for different values of the longitudinal momentum, or for different slices of the longitudinal momentum. So this indeed is like the tomography of our brain, right? Okay, but in momentum space. And this is described by the so-called TMDs, which stands for transverse momentum dependent particle distribution functions, which now depend also on the transverse momentum component. And of course, when we integrate the transverse momentum dependent PDFs over the transverse momentum, we end up with the standard PDFs, okay, which are collinear indeed. The other way of studying the multidimensional structure of protons is to look at the parton densities in the spatial transverse plane. So these are the spatial coordinates, Bx and By. Again, one can obtain this for different slices of the longitudinal momentum function x. Okay, so these two are essentially 2 complementary ways to study the multidimensional structure of protons, and altogether they provide indeed a full phase space knowledge of partons within the proton. These are parameterized by a different family of functions that we call the generalized parton distribution functions, which I will not discuss today for time reasons, but also because the Ferrara group has mainly contributed to the TMD. Okay, but I have some material in the backup if you want to know more. So let's focus on the TMDs. Okay, When we allow now for the momentum, for the transfer momentum of quarks, then we can fill this table. Okay, we not only have the TMD versions of F1, G1, and H1, but we have also 5 additional TMD functions that disappear in the collinear approximation. They disappear if we integrate on the transfer momentum. And each of these has a specific probabilistic interpretation in terms of parton densities. Each of these depends on X, on the utility momentum fraction, and also on the transverse momentum component. Okay, so ideally, if one would know with very high precision both the transverse momentum and X dependence, then you are ready to produce your 3D map of the nucleus, just the one I showed before. Another important thing is that these TMDs actually describe so-called spin orbit correlation within the proton, which are in the form of this mixed product. We have a spin, then a scalar product of a vector product of 2 momenta, and we have a different possible combination that I will discuss later here. And the important point is that this spin orbit correlation generated flavor-dependent distortion of the parton densities. So you look here. This is again the transverse momentum plane, kx over ky. The longitudinal direction is always Z, okay? And you see that if the proton is transversely polarized, this we call the series effect, then the parton density are not isotropic. They are shifted one side. And opposite side for the d quark. So this is also flavor dependent. Okay, so there is a lot of phenomenology here. And in addition, TMDs provide an indirect sensitivity to the angular momentum of quarks, one of the still missing pieces in the spin proton puzzle, right? In the sense that if this Siever effect would be measured to be 0, then by sure angular momentum could be 0. But if the Siever's effect is measured to be non-zero, then for sure there has to be a non-zero quark orbital angular momentum, although we cannot yet quantify it. So the best process to measure TMDs is again semi-inclusive Ignacius scattering. So again, where we detect not only the scattered electron, but this in coincidence with one of the hadron producing the fragmentation of the quark, or the star quark. And we can also see the process in this cartoon here. So the gray plane is the scattering plane. We have the incoming electron, the outgoing electron, the emitted bit of photon, and our target proton. Then something happens here, and then one of these hadrons is produced with a certain angle and a certain momentum. And so we can define this yellow plane here, that's the momentum of the hadron bias. And then if the target is transversely polarized, we can define 2 azimuthal angles, the angle phi between the scattering plane and the hadronic plane, and phi s, which is the azimuthal angle of the target vector, the target polarization with respect to the scattering plane. Now, without going into too much detail, I was mentioning that TMDs encode this kind of spin-orbit correlation, where S, P1, and P2 can be anything. Can be the spin or the momentum of the quark or the proton, etc. So let me just give you some example. The Bohr-Mulder effect, which is sensitive to this TMD function here, okay, the one in this corner here of the table, this describes correlation between the transverse spin and the transverse momentum of quarks within an unpolarized proton. And this kind of correlation, in general, produced azimuthal asymmetries in the direction of the final state hadrons, this hadron here, okay? So one can really measure this effect by measuring the azimuthal dependence in the distribution of these final state hadrons. And in particular, this effect goes like cosine of 2 phi. Phi is this angle here. And we have measured this at Hermes. I will not go into the detail, of course. This is for pi plus, pi minus, k plus, and k minus, which is this hadron here. And overall, we measured, as you can see, a non-zero effect. And this was the first proof that, for instance, this Bohr-Mulder function is non-zero. Okay, we measured it for the first time at Hermes that it is non-zero. Another combination is the Siever's effect, the one that I was just mentioning. In this case, this is sensitive to the correlation between the transverse momentum of the quark and the transverse polarization of the proton. In this case, it is now polarized. See here in this particular. And this generates a sign of phi minus phi s modulation. And again, we have measured this, and again, we've set the non-zero results. And one last example is now the transversity function together with this Collins fragmentation function. This ends up in the so-called Collins effect, which is sensitive to the correlation between the transverse spin of the quark and, in this case, the transverse momentum of the final state hadron. I have to say that there is another group in Ferrara, the group who will take by Giulio and others, Gigi, Isabella, who made in the past a measurement of this Collins fragmentation function, which is, of course, absolutely relevant for this kind of studies. And this is done at the E plus C minus machine. So it was done at Babar and now also in Best 3. Now we also measure this, and again we have a non-zero signal. Okay, so we are happy. Just to make you a bit bored, let's have a look at the full expression of the cross section. So see this semi-Gaussian EIS. We have plenty of terms. I'm not going to be there, of course, but let me show you that each of these terms come with a specific azimuthal modulation in terms of these two azimuthal angles. Okay, sine or cosine or whatever. And then we have terms which are unpolarized, terms which require the beam polarization, terms which require the target polarization, longitudinal or transverse, and terms which require both target and beam polarization. And so, and each of these terms comes with a structure function. So these are now the structure function of the series. There are plenty of them, and each of these is essentially given by the convolution of one of the TMD function and one of the fragmentation function. Okay? This is the one I was mentioning before, as it's measured by industry and Bell. So, again, no detail, but just to say that with Herbes, we have measured essentially all of these contributions here, and also as that this is done by Compass, our competitor, okay, with results which are essentially consistent. So we have indeed now we're starting to have interesting knowledge of the quark TMDs through the semi-Gaussian EIS process. But Compass and Hermes are not the end of the story. There is another laboratory on the other side of the ocean. We are now in the United States, in Virginia, and this is the Thomas Jefferson Lab. And here we have another facility which provides a high-intensity continuous electron beam with energies up to 12 GeV and very, very high polarization, serving 4 experimental holes, A, B, C, and D. And this facility allow actually to map this region here of the kinematic plane, so the large and very large X Bjorken. So we are really deep into the valence region of the problem here. Okay, something that all other experiments cannot just cover. They are just beyond that. And Ferrara is particularly involved in the class 12 experiment, which is in hole B, which is actually the largest detector in the smallest experimental hole, by chance, I don't know why. So this detector is able to cope with the very, very high luminosities, 10 to the 35. It can have a polarized hydrogen and neutron target. It has, as you can see here, a very wide acceptance and also very good particle identification detectors. We have actually a central detector here with the target, and then we have a forward spectrometer based on a torus magnet. This is a picture of the class 12 detector in JLab. And again, there are also important contributions from the Ferrara group here. So we are, of course, persons of different series experiment proposals. We have also covering, maybe in the past, high-level role responsibilities. We are involved in several analyses, in particular, Lorenzo, which is not here today. Then one of the main contributions from Ferrara was actually, together with the international collaboration, of course, was to realize and construct these two rich detectors that cover 2 out of the 6 sectors of class. And the rich detector, as you probably know, is a detector that exploits the Cherenkov radiation, and this is used to separate hadron types, protons, gams, pions, over a momentum range that was in which otherwise they were completely overlapped. And we are also looking into the future. Okay, this is what we call the RGH experiment that we are now starting to develop now. And this will be the very first experiment with the transverse polarized target at class 12. So we are now studying the theogenics, the transverse magnet, the target, and also this recoil detector for measuring the recoil proton. So this is a work in progress. And class is important to set because of this huge luminosity, okay? Huge acceptance, huge luminosity, and this allows indeed to perform multi-dimensional analysis. We have done also in class, in Herbes, but now really, this is a completely another level. You can bin your data in simultaneously in 4 dimensions, okay? And you can really perform four-dimensional extraction of our observable sensitive to the TMDs. Just to give you an idea, you see this, there is a tiny point here in black. They actually have an error bar, but you cannot see it. And you can compare these, which are after just a few weeks of data taking, compared to the previous existing data from previous experiment, including compass areas, etc. Okay. So the expected precision, statistical precision is really huge here. And this allows to make indeed precision multidimensional studies. So what is the status today of TMDs? Again, the TMDs are extracted from the experimental observables and in these sophisticated global fits. And the situation is more or less this one here. So we are starting to have first extractions of the underlying TMDs, the unpolarized, the sievers, the warm gear, the transversity, and so on, the Bohr-Mulders. This is as a function of X. We have also distribution as a function of PT. Still, the precision is limited. As you can see, we have huge uncertainties here and there, and so we are still not ready to make this 3D map, okay? But the direction is now this for the future. And what about gluon TMDs? These will be very fast here. Well, we have quark TMDs, but of course we also have gluon TMDs, and we can accommodate them in a similar table as before. So they have similar naming, similar notation, but of course some very different properties that I will not go into detail here. And we have also already some quite interesting model calculations for gluon TMDs. These are again the density in the transverse plane sensitive to the F1G and G1TG, this one here, or this is the F1G and the Bohr-Mulders for the gluons. But the point is that the experimental access is essentially zero, extremely limited. Okay, we have a strong theory, we have models, we don't have essentially data apart from very few things from compass and on physics. Okay. I don't have time to go to discuss this, but again, I have some material in the backup slides if you want to know. So let me conclude with what are the main open questions in the field and what is the future perspective for the field. So let me come back to this picture here. You remember I draw your attention to the fact that the gluon density was dumped by a factor of 10 in the problem just got. So if you remove the factor of 10, then you end up with this trend compared to all the others. So it seems that the gluon PDFs rises without apparent limit, which is a problem, okay? Because if this is the case, then we would expect a violation of unitarity. So at some point, and we don't know which point, this gluon distribution must saturate at some point. And when it saturates, we end up with a completely gluon-dominated structure of the proton, something that we call the color glass condensate, and something that has never tested experimentally because we don't know when this happens, okay? So one first question is, at which scale the gluon density starts to saturate? When this curve starts to saturate. And then, is there a clear boundary between this gluon-dominated region, the glass condensate, and the standard, the quark gluon matter? We don't know. Other question is related to the mass, okay? So we know that the mass of the quarks is obtained through the Higgs mechanism by interacting with the Higgs field. But if you consider the mass, the bare mass of quarks, then these account only for 1% of the proton mass. So this means that 99% of the proton mass, proton, but also neutron, and so nuclei, and so atoms, and so the entire visible universe comes actually from the gluon self-interaction energy. That is something that is there because gluons also carry color charge, so they must self-interact. So it's a pure vacuum energy that produces the mass of the proton and actually of the visible universe. So how does the mass of the proton emerge from the QCD vacuum? Then we discuss the tomography of the proton, the 3D distribution, okay, TMDs, GPDs, but the information that we have today are limited to valence quarks, up quark, down quark. Okay? We don't know essentially anything about C quarks and essentially anything about the gluons. So this is the next frontier, of course, in the field. Then, one more question. What about these 20–30% of orbital motion? This we cannot measure, but for sure this should be there. Okay, so the question is, what is the role of the orbital motion of quarks and gluons in building up the nuclear spin? Is there a way to access this contribution? And then the last one, how do quarks and gluon distribution and interaction are affected by the nuclear matter? So we know how to measure PDFs of a free proton, but what about if the proton is within a huge nucleus, lead nucleus? Okay, so clearly we get distortions of these. Okay, this is an idea of the distortions we get compared to one. So these are called, let's say, cold nuclear matter effect or nuclear PDFs, but we know very little at the moment. Okay, why do we have this rise here, that we have this low here, and so on? And also, what are the mechanisms that occur when a parton, a gluon or a quark propagate within cold nuclear matter? Okay, so there are many experiments, also at CERN, LXC, that are studying this, but we still know quite little about this. So in order to answer all these questions, what we need is a new generation electron-ion collider with a kind of very strict requirements. So wide central mass energy range, okay, in order to make precision study in this gluon-dominated region that we have not explored enough so far, highly polarized and electron and proton beams, high luminosity in a wide range of central mass energy, just to ensure the capability to make precision multidimensional studies of the nuclear structure. And also, for the last question, the possibility to accelerate nuclei from deuterium up to uranium, okay? So to have indeed a full systematic study of the nuclear matter effect. So the proposed electron-ion collider at Brookhaven in the United States is the ultimate machine to address the question above. The idea is to exploit the existing RIC hadron storage ring and to add an electron storage ring, such to make again collision between electron beam and proton beam or ion beam. Okay. This is more or less the layout of the facility. I will not go into detail again. Just see that this is the polarized ion source, so essentially the ions of the protons are produced here, and then they're injected into the yellow ring. And then we have the polarized electron source, which is then injected into the light blue. And then the two are colliding in two interaction points. And at the moment, we have a plan for constructing a detector only in one of the two interaction points. These are the beam parameters. I will not go into details. This is the range of energy for the beam, for the electron beam and for the proton beam, in order to access this wide range in central mass energy, 20 to 130 GeV. And these are the beam parameters that corresponds to the maximum instantaneous luminosity. What about the detector? The detector must be a general purpose, of course, because we want to do a lot of physics with these beams. It is a collider, so it must have, let's say, a cylindrically symmetric central barrel, but it is an asymmetric collider. We have electron from one side and ions from the other, so this has to be matched with two very specified, very specific and diverse end cap, the lepton end cap on one side and the other lepton from the other side. So this is more or less an overview of the concept of the detector, which is now being actually constructed. So in green, we have the tracking stations, of course, which are needed to reconstruct the primary, secondary vertex and to reconstruct the charge of charged particles. In green, we have the particle identification detectors. And here there is an important contribution from INFN in general and also Ferrara, because we are now involved in the construction of this dual radiator bridge detector. Then we have the calorimeters, okay, the bar and the end caps, and then we have the hadronic calorimeter, and this is the story with also the magnet college. So I'm done. Let me go quickly to the conclusions. So after decades of collinear studies, now the 3D structure of the neutron is now being revealed. Thanks, of course, to an international, huge international effort that see together a traditional experimentalists. A rich phenomenology and also a surprising effect arise when the transverse degrees of freedom are not integrated out. Okay, so when we consider that. And of course, revealing the complex QCD dynamics inside the proton is a complex task, so we need high precision multidimensional analysis and measurements. And so in turn, we need large acceptance, high luminosity detectors, and also we have to keep the systematic uncertainty as low as possible. In the close future, we expect to have the data from JLab in this balance region, so in this large X-Birken region, okay, which is the moment free of data, essentially. And in the next decade, we hope to have the first data from the electron-ion collider, which will mainly cover the opposite region, so very low X, the gluon-dominated region and C-quark-dominated region. And then, of course, all these can work if there is a strong collaboration between experimentalists and theorists, okay? So a solid theoretical framework with sophisticated phenomenological global analysis and also theoretical model are absolutely necessary to interpret the experimental data, to pin down from them the underlying distribution functions in the NGPs. And I'm done. Let me just advertise my PhD course on the neutron structure. So if you like this argument and you want to know more, I will be delivering a PhD course on the phenomenology of the neutron structure in July, so you can subscribe to this class. Thank you.
Very nice lecture.
Bye, Giulio.
Is mostly thank you. It was very, very clear. It's wonderful when one rediscovers the things that one has had to study in the past, but now sometimes I forget. And I go from the experimental measurement and then try to it's a matter of statistics, or are there any difficult interpretation of the data? So it's just a matter of accumulating enough statistics, but we know we fully understand. If we study one process, we fully understand it, and we have to produce it 10 millions, 100 billions of time. So even if I have 1 billion of data, still I will need a strong interpretation of the data to access to those distributions that are less studied.
Okay, clear. So statistics is one phase of the problem. Of course, the more you have, the best it is, clearly. We don't have to forget about systematic uncertainties, which are sometimes larger than statistical uncertainties, especially when we go to these huge luminosities. And systematic uncertainty can arise, for instance, from the limited acceptance of the detector, or can arise from the limited precision in the measurement of the polarization of the target or the beam. Okay. So suppose everything is perfect from the experimental point of view. So zero, uncertainty, statistical, and systematic. Then what the interpretation, what you were saying before. The extraction of these TMDs requires a lot of theory effort there. It's not trivial at all. And one thing that I did not say, just for time reasons, of course, but is that one very complication that arises. Okay, let's do it this way here. What? No, I think I have it. Oh, yeah, here. So each of these structured functions that contain information on the construction, as I said before, but very, very quickly, is a convolution of a distribution function and a fragmentation function. This does not mean that it is a simple product. So you measure these, you know the other, you can immediately get the distribution function. It is a convolution. This means it is an integral over translated momentum. And this integral is not solving numerical, it's not solving analytically. You cannot solve analytically. So here you have to make, for instance, some hypotheses, okay? Either you simplify the distribution, you assume that they are Gaussian in transit momentum, and then you can solve it analytically, or you have to solve it numerically and you introduce new uncertainties. So the business is indeed complicated. It's just an example, but things become even more complicated when we do TMDs, because we call this TMD factorization. It is very, very complicated stuff.
And another curiosity, because I should know it, but probably I don't remember it. How do you pick? You don't pick the hadron at the end. You look for a generic kaon, or do you search for?
No. We have the rich detector, so we are allowed to separate.
No, but you, of course, which of the because you have X.
Yeah, the leading, the one, the highest energy hadron is the one coming from the fragmentation of the stock quark.
Okay.
The other are soft hadrons, and so
so that you have basically a momentum.
Yes, sure, absolutely. Yeah, we measure the momentum energy, and then we select the leading hadron, which is supposed to come from the hard process. Yeah.
And another couple of
sorry, related to this.
We can go to dinner together.
Of course.
Also, jet physics helps in this.
Yes, these are, for instance, these delta G measurement. Is it now? The delta G measurement here, this guy here. This is done main at RIC, and they use indeed the double spin asymmetries in jet production, because the energy is enough to. So they are very good in reconstructing jet and to measure also these symmetrical correlation in the kind of state. So sure, this is also important.
Sorry.
No, it's a fascinating, because then one thing I like, I don't know if I still here, when I did the presentation on quantum science, the question, because most of the time one thinks that X mass is responsible for our mass, while indeed it's not. It's
1%.
So I said the famous sentence, we are not fat, I'm just having too many gluons.
Exactly.
So that. But it's very important to stress this, because at some point one believes that the mass is dominated by the X mechanism. And instead we have something core to understand at some point, that is the proton. We have new physics that are going one way, the other way, but then we don't understand basically
enough the problem. Yes. Oh, yeah.
Can I see F1 again?
F1
Distributions.
the unpolarized PDFs. This one.
Marco, you're trying to do something that is very difficult for you.
I know, that's why I asked.
Why?
So why I don't see anti-down here?
There should be, I don't know why they didn't put in the plot,
Okay,
but
okay.
of course they extract also
Okay,
down.
okay.
Also has, it means also has Quran.
Yeah, I think so, yes. This I think I took from particle of the book. We have plenty, this is not the only one extraction. Okay? There are plenty of these in the market. This I think I took from the
And why is there a bigger uncertainty on the strings than on the charm, for example? Like, I would say it's easier.
Who knows? I don't know. I cannot answer. I don't know. Yes. And also I cannot see better the colors because I'm with daltonics. But okay, I think this is the fan, right? And this
Yes.
is I don't know. Yeah, the sum should be wider. You're right. I cannot answer this.
Maybe it's a matter of the energy that you are investigating there, because maybe it's when you excite the charm better. Do you have a vector meson dominance effect when you excite the electron? When you have the photon?
Sure, we do.
So
Okay, I
how do you compensate? So do you take into account the fact that you can mediate the interaction with
essentially we try to select a kinematic region where they are not dominant. So they somehow contribute as well, but not dominant. It is the low Z up to 0.7. So an exclusive vector meson production actually lies in the high Z region. Z is the fractional energy of the hadron. So we select kinematic region where it is not dominant for sure, but still can enter. But for instance, I think I can show you the pi zero. I'll show you if I have the right plot here. Because these mostly affect, for instance, the pi plus and the pi minus, because you produce a row that decays in pi plus pi minus, which is the exclusive row, etc. But the pi zero are much less affected by this. Okay, and so if we see, let's say, a non-zero signal for the pi zero, then likely this is not vector meson. This is really in this.
So do you, when you go to transverse momentum, you have also the Z instead of when you do see this, but with a strong photon, do you have asymmetries coming from the
Z photon. Not at these experiments. For sure at Hera, yes. At Hera, they had the electromagnetic and the weak contribution interfering. Sure, interfering. So in that case, at high energy, you have both. Sure.
So you also will have at the EIC.
Sorry?
You have also
at the Hadron Collider. Yes. Well, central mass energy is the other 100 GeV. They could contribute. Sure, not dominant. I think they are quite suppressed.
And so, if you have to ask a young researcher from an experiment that measures plus and minus to atoms, what kind of measurement do you like that we report?
We know little about
Collins.
Indeed, we know still little about the Collins function. The Collins is the polarized independent fragmentation function. There are measurements from Babar, from Bell, and I think not from S3.
You have to measure.
From S3
yes.
As well, okay. And then you measure essentially, again, azimuthal distribution of the two hadrons producing the plus mass collision in this case. So, for instance, we know little about the Collins for counts, for instance. We know more about pions, or the dihadron fragmentation function, where a single core goes into two hadrons, and this also is poorly measured at more. So, this is a place where for sure we can get improvement from the fragmentation side.
Because we are doing a program of fragmentation function.
I know. Yeah.
And
I mean, the unpolarized is pretty well known at the moment. Okay.
But now we have also measured. We are. I don't know how much official it is, but let's say that it's official. We are going to measure the polarization of the beam because we also have the sort of term of effect. We are measuring that. So
the polarization of what?
The beam of the electron beam.
Yes.
Because we have long enough run to start seeing the rise of the so-called.
Okay. In your machine.
Yes, and so there is going to be soon a measurement of the first asymmetries.
Great.
But with muons. But
I mean, Compass is working with muons. So
Yeah,
Also,
what is the advantage of using muons instead of electrons?
advantages I cannot say. From the fundamental point of view, there is no difference to the mass, clearly. They exploit the muon beam from the cave piles extracted from the SPS beam of, and is at high energy than forms. So they use it, but I cannot say there is a real advantage of using that with respect to electrons.
And
I think it is a disadvantage that making an electron beam is much easier. You can make it much more intense and so on.
they don't make any
Yes.
larger luminosity.
I think it's an advantage for electrons.
And you mentioned at a certain point that you can also look to data where you have scattering of neutrinos, no?
Yes, this was done mainly in the 80s. In the 70s, in the 80s, neutrino scattering, yes.
In that case, you don't have you can only measure the hadron, not the distribution. You don't have the recording neutrino, no? Or you do.
The neutrino then, if you send the double, it becomes an electron or a muon.
You want to charge current.
So you still detect charged electron. And there are different PDF that enter into the business when you use a neutrino beam for weak interactions that they didn't use.
Okay. So it could completely different set of.
There is no, completely not, but there is one more, for instance, that disappears in the electromagnetic case. But there are no, as far as I know, recent measurements. This is all was in the 70s and the 80s.
Because most of the neutrino beams are. But we will have a very huge source of neutrinos in the next future in the US. Of course, the beam will be too big to provide the collision reasonably, but
if you make also a big proton, maybe.
but can you do? But the Dune experiment will be basically a huge neutrino to proton. So I don't want to give ideas to the people.
Maybe there are already ideas. You use the neutrino beam for doing this kind of.
Dune is such a big experiment.
I don't know if it is really possible, but
don't have
in
the
principle,
time.
one should explore this. Why not?
I don't know if you have enough. You do this, because you cannot do. I don't think you have enough energy to do this. One can explore it.
Yeah.
It's a huge
But let's make a print, Giulio.
Yes, it's an idea like this.
Anything else? So I'm curious, when you analyze a set of data, you take also in consideration of other experimental constraints, or
What do you mean?
because the final purpose is to define these structure functions as a function of all the observables. And so you can cover a given range of quality or quantities, but should guarantee that there is some connection with the measurements performed in other ranges.
Yes, sure. For instance, for extracting the transverse distribution, we measured the Collins effect in series. But the plus minus machine measured the fragmentation function, but then this was at different energies. So in order to extract transverse, we have first to evolve them to the same scale, at the same Q-square scale, so with the Digler question, and only then you can compare them and you can use them to extract the underlying information. So sure, experiments are different energies, but if you want to make a comparison, you have to evolve at the same scale. And this you can do with Digler or with these more complicated transverse momentum equation, more sophisticated.
Can you use lattice? Does lattice provide improvement?
Yes, recently, yes. let's say 10 years ago, I would say no, but now in more recent years, yes. People are starting using lattice 2 CD to make prediction of the TMDs for the first time here, and also GPDs, and also these so-called tensor charge, which is the integral over X of the transversity, and we do see tension with data.
Yeah, of course, because my point is that we have the measurement of phenomenology from G-2 that was 5 sigma away, and we plugged in lattice QCD, and then now
Everything is perfect.
Everything is perfect, and I'm
Right.
starting to worry about also.
Yeah, there are tensions in some cases, but it's of course important to understand the reason for these tensions. So
and mostly the point is the photon, as always. The issue is the photon dress.
Okay, I think we can close the meeting. Thank you. And we'll reconvene in one month.